This is the second video that should help you out with preparing for the chemistry SOL because we're going through the released 2015 chemistry SOL. This problem asks, which element has 16 neutrons, 15 protons, and 15 electrons? I want to show you the pit hole that a lot of students will fall into if they try to rush. 16 neutrons, 15 protons, 15 electrons. They're going to see this 16 and immediately look on the periodic table and look for the 16th element, which is sulfur. But remember that the identification of an element is actually the number of protons, which is the atomic number. So 15 protons identifies which element it is. This is a particular isotope of a particular element, but the 15th element is phosphorus. So make phosphorus bold, and we put it right here because the 15th element is phosphorus, because phosphorus, every phosphorus, no matter how many neutrons or electrons, has 15 protons. Now let's see if we can fill in the rest of the isotope notation so we can get familiar with it. We know that the answer is phosphorus, but it helps us to review some other things because not every problem will be as straightforward if you watch out for the first trick. 16 neutrons. Recall that the number of neutrons does not explicitly go in isotope notation. So 16 neutrons plus 15 protons is 31 as the mass number for this particular isotope of phosphorus. And then you have 15 electrons. So the 15 protons, that's going to go here if it is there at all. Remember that 15 on the bottom for the atomic number is optional. Because 15 is phosphorus and phosphorus is 15, it's kind of redundant to have it there. Just know that it could be. Is this particular species neutral? If the number of protons and the number of electrons is equal, then it's neutral. So there would not be a charge up here. No charge because it's neutral. The next problem asks, which type of chemical reaction is this? We reviewed in the last video the main types of chemical reactions, with the exception of writing out a neutralization reaction, which is also known as an acid-base reaction. So this particular one, let's see if I can identify some things. We've got a pure element here. That's aluminum. We see that it is being reacted with a compound that is silver nitrate. The products of this reaction are aluminum nitrate. I messed up my colors, let me try that again. The products of this reaction are aluminum nitrate, and then you get some pure silver out. So recall that the type of reaction where you have a pure element, oftentimes, reacting with the compound, and then on the other side you get a new compound and then a different pure element out. That would be known as a single replacement reaction. The next problem says, in the formula for barium chloride, barium is written first because it is. Now this is not one of those questions that's asking you about periodic trends and all this other stuff. You learned a lot of things in chemistry. So you might be thinking, well, the size has something to do with it, or it's a single atom, which clearly it is a single atom in there, but the compound has nothing to do with the fact as to why it's written first. Remember that for an ionic compound, the first element is going to be the positively charged one, often a metal. For an ionic species, and then the second element is going to be the negatively charged nonmetal. Let's go back and give those the names that we remember. This is called the cation, and it comes first. The anion comes second. So the cation is oftentimes a metal, with an exception of sometimes it being NH4, which is called ammonium, and then the anion is a nonmetal. And remember that the cation always comes first. So the only reason that barium is written first is because of the standard IUPAC convention that says for ionic compounds, the positively charged ion, the cation, is first, and then the nonmetal is second. The problem says, which of these laboratory techniques is best to separate a solid from a liquid to recover the liquid? You have titration, chromatography, filtering, and vaporization. Titration is a method used to determine the molarity of, or the concentration of an unknown acid or base using a burette. And that's where you have that long, skinny device with the tip at the end, and then you have the stopcock, and you've got all the little markings. It starts off at 0 and goes to usually about 50 milliliters. And then that is held up in a ring stand. And then an Erlenmeyer flask or a beaker is at the bottom. It has your titrant, which is going to be your unknown oftentimes. That is what titration is. Chromatography is a process used to separate substances based on their polarities. Titration, you should think about acids and bases. Filtering versus vaporization. Vaporization is, as a reminder, when a liquid is turned to a gas using the addition of heat. Often, sometimes you can do it isothermically by changing the pressure. But vaporization is, for example, how distilled water is made. Distilled water, you have a solution of, and it would be a solution because it's impure. Suppose you have some water, and it's dirty water with contaminated with like dirt and stuff like that. You can purify this water by vaporizing it, which is effectively boiling it, and then catching the distillate or the water vapor, and then the water vapor can drip down and be collected, and this would be your pure distilled water. But that is actually not how you separate a solid and a liquid to recover the liquid, not generally. This question may not be written the best because you can separate solids and liquids. If this were salt water, you could distill it and then separate the liquid and the salt. But what makes the most sense is filtration. Filtration is most like coffee, where the solid is separated, the solid like the coffee grounds are separated, and then the coffee is recovered through the filter. Which of these is not required to ensure that stock solutions are free from contamination? Let's go through these one by one. It says store all solutions in brown bottles. That isn't true. The color of a bottle is irrelevant for as far as contamination goes. Some bottles are dark or even opaque to help prevent their dissociation via light. For example, hydrogen peroxide is stored in a opaque or not see-through container because light can break it down. Do not place dropping pipettes in stock solution bottles. That is true. You don't want to dip a type pipette into a stock solution. Never return excess chemicals to stock bottles. That is also true. If you accidentally pour too much, don't just pour it back. And replace tops on reagent bottles after use. That is also true. If you don't put the top back on the bottle, something can get inside. And those are all pretty obvious. So the brown bottles thing makes the least sense. Store all solutions in brown bottles, not true. Now, something else that's important, just as a reminder about chemical storage, is always have labels. Labels are obviously used so that people can tell what is inside. Which of these values is most responsible for changing the boiling and freezing points of a solvent? So as far as solvents go, there are some colligative properties whereby, when present, they can change the freezing and boiling point of a solution, or really of the solvent property in the solution. So a colligative property usually comes from, or can often come from, the solute that is dissolved inside. So suppose we have a couple of different solutions. We've got aqueous solutions of, aqueous solutions means they're going to be based in water as a solvent. You've got sodium chloride, magnesium chloride, and iron 3 nitrate. The way that you analyze how colligative properties with ionic substances affect the boiling and freezing point, as far as the biggest change in the boiling or freezing point, is based on the number of particles that the ionic solute has separated into. Sodium chloride separates into sodium and chloride. That is 2 ions. Magnesium chloride separates into magnesium 2 plus and 2 chloride minus ions. The total number of ions is actually 3 ions in that solution per mole of solute. And then iron 3 nitrate separates into an iron 3 ion and 3 nitrate ions, where a total of 1 plus 3 is 4 ions. So the one that actually produces the most ions in solution is the iron 3 nitrate, and this is the one where if you have a constant 1 mole of solute, 1 mole of solute, and 1 mole of solute, and the normal boiling point of water is 100 degrees Celsius, you would expect the largest deviation from the normal boiling point, or opposite case freezing point, for this solution, because it produces the most ions, and 4 ions will interfere the most with the normal situation that water would be in if it were pure. So the molar mass of the solvent is irrelevant. The electronegativity of the solvent is also irrelevant. The weight of the solute is irrelevant, because adding more will change the property, but only because you're adding more ions to it. What is going to really matter is the number of solute particles. This is 2 particles, this is 3 particles, this is 4 particles per mole of each one. What is the name of the compound with the formula NH4NO3? Naming is a hurdle that a lot of people struggle to get over. They may not be totally comfortable with. But this particular substance is ionic, even though it does not have a metal in it, because one of the exceptions that you had to remember is what NH4 is. NH4 is ammonium. And NO3, as you remember the Nick the Camel thing, is nitrate. This really just comes down to, if you remembered and practiced naming, there are no tricks here. This particular problem isn't asking you to determine the oxidation state of a transition metal or anything like that. It is simply ammonium nitrate. Nitrogen nitrate makes no sense. Nitrogen, hydrogen, oxygen is something that someone could pick up. They're just trying to name the elements in there. And ammonium nitrogen trioxide also would be not a good answer. So the best answer and the only answer is ammonium nitrate. Let's practice something else that people are going to possibly see again. How would you name this particular substance? It would be Cu NO3, 2. Remember that with naming, you take the two pieces and you break them up. Copper is a transition metal, so we're going to call it copper something. We don't know what that copper something is, but in the formula unit, there's simply one copper atom. Looking at the other half, or the anion, you've got two nitrates. So it'll be NO3. Remember that nitrate has a -1 charge. The total amount of negative charge is -2. And because the overall species is neutral, the total amount of positive charge must be +2. And since there is only one copper atom, or just one cationic species in the formula unit, it must provide all of that 2+ charge. So the name of this would be copper 2 nitrate. A couple of other polyatomics that you have to remember. You have sulfate. I'm just going to write the formula out. SO4, 2- is sulfate. Phosphate is PO4, 3-. You got acetate, you have nitrate. Acetate can be written a couple of ways. C2H3O2-. And that's the acetate ion. It's basically like vinegar minus a hydrogen atom. This one asks, calculate the number of moles of lithium phosphate and 2.2 liters of a 0.60 molar solution of lithium phosphate. This is another molarity problem. Molarity is an important concept. Remember that molarity equals the moles of solute, which is what you're dissolving, divided by the liters of solution, which is most of the time going to be water. Let's find what we can find in the problem. We're solving for number of moles. We already know that the number of moles of the solute, which is lithium phosphate, we do not know. We do know the molarity. The molarity is given here. It is 0.60 molar. And the volume of the solution is 2.2 liters. Now we have already done a molarity problem where we had to calculate, I believe that was the molarity itself, and the volume was given in milliliters. Here we've got liters, which is super good. Here we've got molarity, which is just going to be molarity. So all you got to do now is practice your algebra skills and rearrange this to solve for moles. To get the moles alone, you need to multiply both sides by liters. So molarity times volume, in this case liters, is equal to the number of moles of lithium phosphate. It does not matter the molar mass of lithium phosphate because we're solving for moles. If we were asked to solve for grams, we'd have to use the molar mass once we found the moles. But this problem is actually simpler than most molarity problems we did in class. 0.60 molar is the solution, molarity. The volume of the solution in liters, no transitions required from milliliters or vice versa, is 2.2. And I'm going to get my calculator out. I'm going to do 0.6 times 2.2. I got 1.32. And that would be moles. And I'm going to double check my calculation, and it says 0.6 times 2.2. Now let's review sig figs again, because even though this problem doesn't specifically ask for sig figs, and you will probably get your points if you don't do the sig figs, we're going to do it anyway. How many sig figs are in 2.2? That is 2 sig figs. How many sig figs are in 0.60? That trailing 0 on the end is significant based on the rules of sig figs, meaning that there's a decimal point, so that any zeros at the end do matter. So that is 2 sig figs. Between 2 sig figs and 2 sig figs, you're going to need 2 sig figs. Our answer gives us 3 sig figs, so we need to cut it down to be 1.5 0.3 moles. One more example in this video before I make another one that continues on with where we were. Equilibrium has been reached for the reactions shown. Which conclusion is correct? You have a reaction that is nitrogen plus fluorine creates nitrogen trifluoride. And this is a gas phase reaction. With gas phase reactions, pressure matters. For gas phase reactions, you could think of the pressure as sort of like the concentration. If this were an aqueous reaction, concentration or molarity of the solute could be altered by adding more solute or removing solute or some other kind of physical process. But because this is a gas phase reaction, we need to understand that pressure matters. So for gas phase reactions, the first step that I always do is to just count the number of moles of gases on each side. So I divide it down the middle, and I ask how many moles of gas are on the left. The left side total has 1 plus 3, which is 4 moles of gas. The right side has simply 2 moles of gas, because there's a 2 up here. So it'd be 2 moles of gas total. So now we're going to see what the questions are asking, because this is one of those problems where you have to read every question carefully because it's really asking a bunch of different things. The nitrogen and fluorine together will form at a faster rate than the NF3. Let's talk about what equilibrium means again. Equilibrium means the forward reaction is equal in rate to the backwards reaction. Equilibrium does not mean that the reaction has stopped. At least it seems to have stopped macroscopically to our eyes. Equilibrium does not mean everything stops. Equilibrium really just means that if you take 5 steps forward, you're also taking 5 steps back. If you continue to take 5 steps forward and start 5 steps back, you're not standing still, you're just not going anywhere, if that makes sense. So your equilibrium means the forward rate is equal to the reverse rate. Equilibrium can be disturbed according to the Le Chatelier principles. So the nitrogen and fluorine together will form at a faster rate. We're going to say no to this. The whole concept of equilibrium is that the nitrogen and fluorine creation rate is equal to the NF3 destruction rate. They're opposite, but just equal. The partial pressure of nitrogen, fluorine, and NF3 will stay constant. This sounds like a good answer for us so far. Partial pressure is like concentration. If in the solute world, partial pressure is if this reaction is at equilibrium, everybody should be kind of staying where they are as far as their values go. NF3 will form at a faster rate than N2 and F2 together. That does not seem like a good answer because we just said that equilibrium is not about one outweighing the other. Their directions are opposite and equal. The partial pressure of NF3 will keep changing. If it's at equilibrium, which can be represented like this, then the answer will be no. So if I'm going to draw the 3 species, we're going to have no N2 at first, and we're going to, let me go back for this. We're going to have no NF3 at first, and then it's going to be created. So this green line might represent nitrogen trifluoride. We're going to have only N2 at first, and it's going to be destroyed in the consumption, or it's going to be consumed while making the nitrogen trifluoride. And then we are going to have some NF3 is also going to be consumed. And these values, this is completely not to scale. But the concept of equilibrium is that the values are after a while going to remain constant. So you pretend like these lines are all straight. That does not mean that they have fallen to 0, and they certainly will not just be equal, but they are no longer changing. So the only one that makes sense is the partial pressures will stay constant. And in an equilibrium diagram like this, pressure would be the value that would be changing because it is a gas phase reaction. And once it reaches equilibrium, all the values should even out or level out, not be equal, just be non-changing. So that was the last example for this video. On the next video, I'll continue with this problem.